So continuing on, if we take our answer for what sine of theta is equal to and plug it into this formula here for what the area of the parallelogram is equal to, then obviously the modulus of A times the modulus of B is going to cancel, because out of this square root from the denominator here we can pull out the modulus of A squared, modulus of B squared, to get that this is 1 over the modulus of A times the modulus of B times the square root of the numerator here. And of course that 1 over the modulus of A times the modulus of B will cancel with the times modulus of A modulus of B that we've got up here. So that means that the area is just going to become equal to the square root of what we have in the numerator here. And I've expanded this now, so we've got the square root of the modulus of A squared times the modulus of B squared. I've substituted in what the modulus of A squared and the modulus of B squared are in terms of the components of A and B. So of course the modulus of A squared is equal to A1 squared plus A2 squared plus A3 squared, and the modulus of B squared is equal to B1 squared plus B2 squared plus B3 squared. So we need to multiply those two together, and we need to expand that bracket. And then I have taken this second part and I've written it out like this, and the reason I've done that is so that it will be easier for us to expand this bracket. So it's just minus a1b1 plus a2b2 plus a3b3, and then I've written the whole thing out again, times a1b1 plus a2b2 plus a3b3. So now expanding these brackets, we get this huge mess here. So let me just talk you through this. So we'll start with these two here. So we start with a1 squared and we want to multiply that by b1 squared plus b2 squared plus b3 squared. That gives us this first line here. So we get a1 squared, b1 squared plus a1 squared, b2 squared plus a1 squared plus times b3 squared. Then we want to multiply a2 squared by all of these three in turn as well, and that gives us this line here, a2 squared b1 squared plus a2 squared b2 squared plus a2 squared b3 squared. Finally, we want to take this one, a3 squared, and multiply it by all of these three things, so we get a3 squared b1 squared plus a3 squared b2 squared plus a3 squared b3 squared. Then we want to subtract what these two brackets multiplied together expanded is equal to. So we need to take this one and multiply it by all of these three. So we'll get a1 squared b1 squared, and we've got a minus there. Then we'll get a1 b1 a2 b2, and we've got a minus there. And we'll get a1 b1 a3 b3, and we've got a minus there. Then we want to take this one and multiply it by all of these three, and we'll get minus a2 b2 a1 b1 minus a2 squared b2 squared minus a2 b2 a3 b3. Finally, we take this one and we multiply it by all of these three, and then we're going to subtract all of those off. So we'll get a3 b3 a1 b1 minus a3 b3 a2 b2 minus a3 squared b3 squared. Now clearly some of this will cancel. So let's now cancel and simplify. So firstly, the terms that I've crossed off in red here are the ones that completely cancel. So this a1 squared b1 squared, we have over here a minus a1 squared b1 squared. So those two cancel each other out. Similarly, a2 squared b2 squared, we have a minus a2 squared b2 squared here. So those two cancel each other out. And finally, a3 squared b3 squared, we have a minus a3 squared b3 squared here. So those two cancel each other out. Now to simplify what's left, so firstly, note in this bottom half here, there are some terms that are exactly the same, which I've underlined in the same colour. So here we have a minus a1 b1 a2 b2, and here we also have a minus a2 b2 a1 b1. Now they may be written in slightly different orders, but these two are in fact the same term. Similarly in green here, a1 b1 a3 b3, and here we have an a3 b3 a1 b1. Those two are the same terms, so we have minus two lots of that. Similarly in yellow, we have here a2 b2 a3 b3, and here we have a3 b3 a2 b2, so those two are the same terms. So in fact we can collect these ones together. Finally, we can simplify this quite brilliantly by noting the connection with terms in the top bit here. So I've underlined the terms that are going to collect together to make something beautiful. So up here we have a1 squared b2 squared plus a2 squared b1 squared, and this, I claim, can be collected with these that we've underlined in blue here to make this structure here. So if you look at this, a1 b1 minus a2 b1, and if you square that and you expand that, you'll get a1 squared b2 squared, which is up here, plus you'll get a2 squared b1 squared, which is this bit, and then you'll get minus 2 lots of a1 b2 a2 b1, which will give you these things here. So all of what's in blue here can be written as this bit here. Similarly, for in green, we can put these four terms together into this bracket here. So a1b3 minus a3b1, if you squared, if you expand that, you'll get a1 squared b3 squared, you'll get plus a3 squared b1 squared, which is this bit squared, and then you'll get minus 2 lots of a1 b1 a3 b3. So all of what's in green becomes this. And finally, for yellow, a2b3 minus a3b2 squared, if you expand that, you'll get a2 squared b3 squared plus a3 squared b2 squared minus 2 lots of a2 b2 a3 b3, which is this bit here. So all of what's in here can actually be written as this. And why is this so brilliant? Well, you'll notice that these things inside the brackets, these are the components of the vector cross product formula that we saw earlier. And therefore, if you square them and add them together and take the square root of that, that gives you the modulus of the cross product vector. So here we have found that the area of our parallelogram is indeed equal to the modulus of that cross product formula.